You know that feeling when you're staring at a massive spreadsheet, just a sea of data, and you're thinking, where do I even start? Well, what if I told you that hidden inside all that chaos are patterns, these natural groups just waiting to be found? Today, we're going to explore how to find them, how to bring a little order to all that chaos.
Think about it. When you walk into a grocery store, you don't see a random pile of food, right? Of course not. Your brain instantly sees the groups. Okay, apples are here, oranges over there, lemons in their own little spot. You are clustering all the time, without even trying. It's this incredible, intuitive thing our brains just do.
But what happens when it's not a few dozen pieces of fruit? What if you're looking at millions of customer records, or sensor readings from a factory, or a billion social media posts? How in the world can we teach a machine to do that same intuitive grouping our brain does so effortlessly?
Well, the answer is this amazing technique called clustering. On the left, that's what a computer often sees first, just a total jumble of data points with no labels, no instructions. But after we work some magic with a clustering algorithm, we get what's on the right, these neat, distinct, and actually meaningful groups. It's kind of like flipping a light switch in a dark room. Suddenly, everything makes sense.
So here's the key idea, the absolute core of it all. Clustering is all about finding similarities. The whole goal is to create groups where everything inside a cluster is super similar to each other, but really, really different from the stuff in all the other clusters. And the coolest part? It does this without any pre-existing labels telling it what to look for. It finds the patterns all on its own.
So, how do we actually do this? Well, there are a bunch of different tools for the job, but let's start with maybe the most famous one of them all, a real workhorse in the field, the K-means algorithm.
I want you to think of K-means as a very methodical but slightly clueless party planner. You know? Before it can start arranging all the guests into nice little conversation groups, it needs you, the host, to tell it one crucial thing. Exactly how many tables should I set up? That number, that's the K in K-means. And it's the most important decision you're going to have to make.
Okay, so once you give it that magic number K, the algorithm does this simple little repeating dance. First, it just randomly plops K starting points, which we call centroids, right into your data. Then step 2, every single data point gets assigned to whichever centroid it's closest to. Step 3, each centroid recalculates and moves to the dead center of all the points that were just assigned to it. And then step 4, you just repeat steps 2 and 3 over and over again until everything stops moving.
Words are one thing, but let's actually watch this unfold. We've decided we want to find two groups, so we're setting K equal to 2. The algorithm kicks off by just dropping 2 centroids, those red and green stars, at totally random positions. And now for that first big step, the assignment. The algorithm looks at every single data point and asks a simple question. Am I closer to the red star or the green star? And just like that, you get your first 2 groups.
But remember, those first spots were just random guesses. So now the centroids have to move. The red star shifts right to the center of gravity for all the red points, and the green star does the same for the green ones. They're finding a better home. And now, the loop begins. The points get reassigned to the new, better centroid locations. Then the centroids move again. This little assign and move dance goes on, until the centroids finally settle down and stop moving. At that point, the algorithm's done. It's converged, and bam, we have our final clusters.
That looks pretty good, right? But it brings up a huge question. How did we know to choose K equals 2? I mean, what if the right answer was 3, or 4, or 10? How can we know if we picked the right K and made good groups?
Well, to figure this out, we can use a really cool trick called the elbow method. Basically, we run K-means a bunch of times with different Ks. K equals 1, K equals 2, K equals 3, and so on. This chart shows how much better the clusters get as we add more. A lower score is better. Now you'll see the score improves a lot at first, but then it starts to flatten out. We're looking for that sharp bend, that elbow, right here at K equals 3. That's our sweet spot. It's the point where adding more clusters just doesn't give us much bang for our buck anymore.
So K-means seems pretty great. It's simple, it's efficient, it's pretty smart. But, you know, every hero has a weakness, a kind of kryptonite. And for K-means, it has a very specific one that can cause some really bad results.
Its biggest weakness is outliers. Take a look at this data. We can all pretty clearly see 2 groups, right? But then there's that one lonely point way off to the side. To our eyes, it's obviously an odd one out. But K-means it doesn't see it that way. Let's see what happens.
Oh, wow. See?
Because k-means is based on averages, that single outlier acts like a powerful magnet. It literally drags the green centroid way out of position, far from the true center of its cluster. The final groups are completely skewed. They don't reflect the real structure of the data at all. One bad apple really did spoil the bunch.
So, if k-means stumbles with outliers because of how it uses averages, what's our move? Well, we need an algorithm that thinks about the problem in a totally different way. Not about averages, but about density. So let's meet our second hero, a clever density detective called DBCASCO.
DBCBS's whole approach is just fundamentally different. It's not looking for a center point. Instead, it's looking at how crowded each point's neighborhood is. It puts every single point into one of three buckets. A core point is in a really dense, crowded area. A border point is kind of on the edge of a crowd. And noise? Well, that's any point that's isolated, all alone.
Here's how that works. We give DBSCAN two settings, a search radius and a minimum number of points. A point is a core point if it has at least that minimum number of neighbors inside its radius. A border point isn't dense itself, but it's close enough to be a neighbor of a core point. And any point that's not a core or a border point, it's just noise. And here's the absolute best part. We don't tell DBSCAN how many clusters to find. It discovers them all on its own based on these density rules.
The way it works is so clever. It just picks a random point and checks if it's a core point. If it is, boom, a new cluster is born. Then the algorithm expands outward from there, like a ripple in a pond, finding all the connected neighbors and adding them to the group. It just keeps growing until it hits the edge of that dense region. And any points that are left over at the end, they get labeled as noise. Our outlier problem solved.
Okay, so now we have two really powerful algorithms in our toolkit, k-means and DBSCAN. And the question isn't which one is better. The real question is which one is the right tool for your specific job.
And this is where DBSCAN really shows off. Look at this data set. It's basically two rings, one inside the other. Poor k-means has no idea what to do. It's built to find round, blob-shaped clusters, so it just chops it in half. It fails completely. But DBSCAN, our density detective, it sees two separate rings of high density and nails it perfectly. This is its superpower, finding clusters of any weird shape you can throw at.
So let's break it down. When should you use which? K-means is your go-to when you have a pretty good idea how many clusters you're looking for and you expect them to be kinda compact and ball-shaped. It's super fast and simple. But if your data is noisy, or if you think the groups might be weirdly shaped, or if you have no clue how many clusters there are, DBSCAN is, without a doubt, the superior choice.
So we've seen how we can teach machines to find hidden structures in data, turning what looks like chaos into something clear and understandable. I mean, this stuff is used everywhere, from finding groups of customers from marketing, to detecting credit card fraud, even to grouping galaxies by their shape. So the next time you're faced with a giant pile of complex information, maybe ask yourself what hidden groups are just sitting there waiting to be discovered.